In this video, we're going to discuss elementary row operations of a matrix. Let m, n be positive integers. Let A be an m by n matrix. An elementary row operation on A is any one of the following procedures on the rows of A. Interchange two rows of A, multiply a row of A by a non-zero constant, add a multiple of a row of A to another row of A. Interchanging two rows of A is known as a type 1 elementary row operation. Multiplying a row of A by a non-zero constant is a type 2 elementary row operation. Adding a multiple of a row of A to another row of A is a type 3 elementary row operation. Let's look at some examples. Example: let A be the matrix whose first row is 1, 2, 3, 4, 5. Second row is 6, 7, 8, 9, 10. Third row is 11, 12, 13, 14, 15. The matrix 6, 7, 8, 9, 10, first row, 1, 2, 3, 4, 5, second row, 11, 12, 13, 14, 15, third row, is the result of applying the elementary row operation R1 interchange R2 to A. You're interchanging rows 1 and 2 of A to obtain this matrix. Here, R1 interchange R2 denotes that row 1 and 2 of A are interchanged. Observe that R1 interchange R2 is a type 1 elementary row operation. Another example. Let A be the same matrix of the previous example. The matrix 1, 2, 3, 4, 5 first row, 6, 7, 8, 9, 10 second row, 55, 60, 65, 70, 75 third row is the result of applying the elementary row operation 5R3 to A. In this case, 5R3 denotes that row 3 of A is multiplied by 5. 11 times 5 gives you 55, 12 times 5 gives you 60, up until 15 times 5 gives you 75. 5R3 is a type 2 elementary row operation. Another example. Let A be the same matrix of the previous two examples. The matrix 25, 30, 35, 40, 45, first row, 6, 7, 8, 9, 10, second row, 11, 12, 13, 14, 15, third row, is the result of applying the elementary row operation R1 plus 4R2 to A. Observe that our first row of the matrix is the same as the original row 1 added to 4 times row 2. Let's look at that right now. So row 1 plus 4 times row 2. Now, row 1 was 1, 2, 3, 4, 5. Now I'm multiplying 4 times row 2. Row 2 was 6, 7, 8, 9, 10. So this is equal to still row 1 plus the following row matrix. 4 times 6 is 24. 4 times 7 is 28. 4 times 8, 32. 4 times 9, 36. 4 times 10, 40. Our result is 1 plus 24 is 25. 2 plus 28 is 30. 3 plus 32 is 35. 4 plus 36 is 40. 5 plus 40 is 45. So observe that the first row of our resulting matrix is derived from taking the first row of A and to it adding 4 times the second row of A. So let's read. The matrix that we obtain is the result of applying the elementary row operation R1 plus 4R2 to A. Here, R1 plus 4R2 denotes that 4 times row 2 of A is added to row 1 of A. R1 plus 4R2 is a type 3 elementary row operation. Okay, so let's summarize our notation. When we write Ri interchange Rj, or you could say Ri interchange with Rj, that denotes that rows I and j of a matrix are being interchanged. When we write Cri, that denotes that row I of a matrix is being multiplied by the constant C, or by C simply. Rj plus Cri denotes that C times row I of a matrix is being added to its jth row. Example, using elementary row operations to solve a linear system. So what we're going to do here in this example is do the familiar mechanics. Write the augmented matrix of the system and then use those row operations we just studied to come up with solutions of the system. In this case, we have two equations, two linear equations, 3 variables, so we're expecting there might be more than one solution. Okay, so let's turn to the camera. So here is our augmented matrix. So we write the coefficients and then the right side. So the coefficients are 1, 3 for first column, 1, 3 for first column, 3, 4 for second column, -7, 2 for third column, and then the right side is 12, -4. Let's begin by eliminating these 3. We want a 0 here. So what we do is we take that row, the second row, and subtract from it 3 times the first row. So take the second row, which is R2, minus 3 times R1. Okay, so here's what we get. Row 2 minus 3 times row 1. So that's a row 2 minus this row matrix. 3 times 1 is 3, 3 times 3 is 9, 3 times negative 7 is negative 21, and 3 times 12 is 36. The result is 3 minus 3 cancel out, gives you 0. 4 minus 9 gives you negative 5. 2 minus 21 is 2 plus 21, which is 23. And then negative 4 minus 36 is negative 40. So my result replaces my second row. 0, negative 5, 23, negative 40. Okay, next. Let's try to get rid of that 3 over there. We can get rid of the 3 if we carry out the following elementary row operations. First, make this a 1. So multiply row 2 by negative 1/5. And then later, once you have a 1 here, you take a row 1 minus 3 row 2. But there is a more direct way of doing this. What about if I took row 1 and to it add 3/5 row 2. So here we have row 1 plus 3/5 row 2. What do we get from that? 1 plus 0 is 1. 3/5 times negative 5 becomes negative 3. 3 plus negative 3 cancels out. Mission accomplished. Negative 7 plus 3/5 times 23 is negative 7 plus 69/5. Now, here, if we multiply top and bottom by 5, we end up with 69 minus 35 all over 5, which is 34/5. Now we have 12 plus 3/5 times negative 40. The 5 and the 40 cancel, so you end up with 3 times negative 8, which is negative 24. 12 minus 24 is negative 12. Okay, so here's what we did. We took row 1 plus 3/5 row 2, and that gives us 1, 0, 34/5, negative 12, and then our second row is that. Okay, so now notice that right here we have two equations at this point. You have x1 plus 34/5 x3 equals negative 12, and then you have negative 5x2 plus 23x3 equals negative 40. If you're going to solve for x1 and x2, you would like there to be a coefficient of 1 in x2. So my last step should be to make this a 1. So multiply row 2 by negative 1/5. let's look at that in the notes. So multiply our second row by negative 1/5. So we end up with 0. Negative 5 times negative 1/5 gives me 1. 23 times negative 1/5 gives me negative 23 over 5. And then negative 40 times negative 1/5 gives me 8. So now I have x1 equals negative 34 over 5. x3 minus 12. And x2 equals 23 over 5. x3 plus 8. x3 will be any real number. Now, we write this. Now, our solution set consists of all triples, where our x1 value is negative 34 over 5 t minus 12. Our x2 is 23 over 5 t plus 8. And our x3 is t, where t is any real number. Now, let's see a graphical representation of this. We were solving a system of two linear equations in three variables. Graphically, each of these systems represents a plane in R3. What we obtain is all points of intersection of the two planes. Let's observe here in this graphic, in this graph. So here we have the graph of our linear equation x1 plus 3x2 minus 7x3 equals 12. And we also have the graph of 3x1 plus 4x2 plus 2x3 equals negative 4. Their intersection happens to be that line, and that line is described by all the set of all points in R3 with this parametric description. All right, here we have some exercises for the audience. So one, let A be the matrix whose first row is 3, 4, 5, 3, whose second row is negative 2, 0, negative 3, 1, whose third row is 1, 2, negative 2, 2. Apply a chain of elementary row operations one at a time until a reduced row echelon form matrix is obtained. 2. Solve the given linear system. So this is similar to our second example. If you want, you can pause the video. I'm going to display solutions. So spoiler alert. Solution to number 1. It continues. Do note that steps may vary, but the answer will not. Regardless of how you take your steps of elementary row operations, at the end you should get this same result you see on the bottom right. And now the solution to the second problem. Okay, that's all for now. Thank you for watching.